All right, let's dive into something that's, at the absolute core of modern mathematics, the function. But I want you to forget all those dry formulas for a minute. We're going to look at functions for what they really are, these powerful, elegant machines designed for mapping one world to another. Let's do this.
I mean, for a lot of us, that first time we saw f of x in a textbook, it felt pretty abstract, right? What is it actually doing? Well, today we're going to figure that out by building our very own function machine, right from the ground up.
Okay, so picture this. A function is a machine. You drop something in one side, that's your input, and it comes from a set we call the domain. The machine then follows one specific rule, whirs for a second, and spits something out the other side, that's your output, which has to live in another set called the codomain. It sounds simple enough, right? But here's the catch. For this machine to actually work, it has to follow some very, very strict rules.
And that brings us to the first part of our journey. Before we can do anything cool with our machine, we have to make sure it's well-defined. What that really means is, it has to obey 3 non-negotiable golden rules. These rules are what keep it from jamming, malfunctioning, or just plain breaking down.
So first up is a rule called totality, and this one's pretty straightforward. If your machine says it can handle inputs from a certain domain, then it has to be ready for all of them, every single one. You can't just have an input that the machine, well, ignores. Every element from the domain needs to have a place to go.
So what happens if we break this rule? Let's take a look. Imagine our machine's rule is g of x equals 1 divided by x minus 1, and we tell it the domain is all real numbers. Okay, so what happens when we try to feed it the number 1? Well, we get 1 divided by 0 and boom, the machine just jams. It completely freezes. It has no output for that input, so it fails the totality test. It's not a well-defined function, at least not on that domain.
The second golden rule is existence. This one means that whatever our machine produces, whatever comes out the other side, has to land in the designated output area, the codomain. It can't just spit out random things that don't belong. The output has to be a valid member of the club.
Here's a perfect example of that. Let's say our machine is supposed to take a natural number, 1, 2, 3, and so on, and map it to another natural number, using the rule f of n equals n minus 1. Simple enough? But what happens if we put in the number 1? The output is 0. But wait a minute, 0 isn't a natural number. Our machine just produced an invalid output, one that's totally outside the specified codomain. That's a system error. The existence rule is officially broken.
And that brings us to our final and maybe most important rule, uniqueness. This rule is really the heart of what makes a function so reliable. When you put something in, you have to know with 100% certainty what is going to come out. One input, one and only one output. No confusion, no ambiguity, no maybe this, maybe that.
Now, this is where a failure of uniqueness can get really sneaky. Imagine a machine that takes any decimal and gives you its first digit. Okay, what do we do with 0.5? The first digit is 5. Easy, right? But here's the thing. Mathematically, the number 0.5 is the exact same number as 0.499 repeating forever. So, should the output be 4? Now we've got a single input, the number 1/2, with 2 different ways to write it, leading to 2 totally different outputs. That is a classic malfunction. It breaks the uniqueness rule, and it's no longer a well-defined function.
Okay, deep breath. Our machine is now well-defined. It's reliable, it doesn't jam, and it follows all 3 golden rules. So now, the fun part begins. We can start adding some really powerful upgrades. Now, these aren't required for a machine to be a function, but they give it some special and incredibly useful properties.
We've got 2 main upgrades to choose from. First, over on the left, we have injective, which you might also hear called one-to-one. This just means that no 2 different inputs will ever lead to the same output. Think of it like this. Each target in the codomain gets hit by at most 1 arrow. Then, on the right, we have surjective, or onto. This means that every single possible output in the codomain is actually used. No target is left untouched. Every target gets hit by at least 1 arrow.
So, how do you actually prove that a function has this cool injective upgrade? It's kind of a neat logical trick. You start by assuming the opposite, that 2 inputs, let's call them x1 and x2, do give you the same output. Then, you just use algebra to work backwards. And if the only way for that to be true is if x1 and x2 were actually the same number to begin with, then you've just proved it. Different inputs must give different outputs. Your function is officially injective.
All right, now for something really amazing.
We have our well-defined machine. We know about our two optional upgrades, injective and surjective. So the big question is, what happens if we install both of them at the same time? Well, we get the ultimate function machine.
A function that is both injective and surjective gets its own special name. We call it bijective. This, right here, is the gold standard of functions.
Let's really think about what this means for a second. Injective means every output has at most one arrow pointing to it. Surjective means every output has at least one arrow. So when you put them together, what do you get? You get a perfect pairing. Every single output has exactly one arrow pointing to it.
And this is the formal definition of a bijective function. It creates a perfect one-to-one correspondence between two sets. Every single element in the domain is uniquely paired up with an element in the codomain, and every single element in the codomain is accounted for. There are no duplicates and no leftovers. It is a perfect match.
And here it is, the grand finale. Because every arrow represents a perfect, unique pairing, we can just reverse all of them. A bijective function is invertible. We can build an inverse function, which is often written as f with a little -1 exponent, that works as a perfect undo button. It takes every single output and maps it right back to the unique input it originally came from.
And this is the key theorem that just ties a bow on the whole thing. A function is perfectly reversible, meaning it has what's called a two-sided inverse, if and only if it is bijective. This isn't just a happy coincidence, it's a fundamental truth of mathematics. Being both injective and surjective are the exact, precise conditions you need to build a machine that can run in reverse. So just like that, we've gone from a simple machine with a few rules all the way to a perfectly reversible one. And this isn't just some abstract math puzzle. These ideas are the engine running behind data compression, they're the security backbone in cryptography, and they power countless algorithms in computer science. It really makes you wonder, doesn't it? What other complex parts of our world are actually built on such simple, elegant foundations?